Okay, today we'll get a little bit more into this standard reduction potential. So we'll call this strengths of oxidizing and reducing agents. A couple things about this. We kind of just went over this in the homework, but the more positive the E0 reduction value, the stronger the oxidizing agent is. The opposite is true as well, that the more negative the E0 reduction potential, the stronger the reducing agent. Stronger the reducing agent. So, real quick, turn in your book to page 857, and if we check out page 857, we'll see that the strongest reducing agent is the half reaction involving fluorine. The strongest oxidizing agent would be the half reaction involving the lithium ion and lithium. Obviously, positive 2.87 for the fluorine, negative 3.05 for the lithium. So, we would say here that F2 is the strongest oxidizing agent. At 2.87 volts. And we would say that the Li plus ion actually I'm going to call it the Li atom is the strongest reducing agent at negative 3.05 volts. So if we said here, use table 20.1 to rank the following in terms of increasing oxidizing agent strength. We're increasing oxidizing strength. And let's say that we had these ions, NO3 negative, Ag plus, and chromate, Cr2O7 negative, 2 minus. Okay, if we were given these and we wanted to rank them in order of increasing oxidizing strength, what we essentially need to do now is find the standard reduction potential for the half reactions that those are involved in table 20.1. What did you find for, what is E0 for NO3 negative? 0.96 volts for Ag plus, somewhere around 0.80 I believe. And what about for chromate? Yep, and we want to rank them from order of increasing oxidizing strength, so we're going to go Ag plus is greater than the NO3 negative, which is greater than the chromate Cr2O7 2 minus. Just like that. And an important thing to remember is that any metal in the standard reduction potential table will be oxidized by the metal ions above it. And the other thing that's important to know is changing the coefficient of a half reaction will not affect the standard reduction potentials. So coefficients do not affect the E naught values. So for silver, as an example here, if I just take a look, and we have Ag plus an electron yielding Ag, and the E naught value is equal to 0.80 volts. If I multiply through by 2, I'm still going to get here an E naught value of 0.80 volts. Both of those have the same value, so we're unaffected here by a change in the coefficient. Okay, and just to be aware of where you find these values more extensively, Appendix E, in the back of your book has the extensive list for E naught values, and that's where you want to take a look to find when you're doing your homework. A lot of times you can find them on table 20.1, but in the back of the books, Appendix E is better. No problem. Yeah, there is good. Did you get that? Okay. So let's use Appendix E to answer the following. Let's say that a voltaic cell is based on a cobalt ion and atom half reaction and a silver and silver ion half cell. First thing we want to do here is write the half reactions that occur at the anode and cathode. Okay, so we want to write the half reactions that occur at the anode and cathode, and also find E naught for the cell. So one thing that is important to keep in mind is that the more positive E naught value serves as the cathode when we're dealing with two half reactions. Right, so this is going to serve as the cathode. So the first thing that is helpful is to go into Appendix E and take a look at the system that we've essentially been given, Ag plus to Ag, CO2 plus, CO2 cobalt ion to cobalt. And let's get the E naught values associated with those two. So what do we find when you take a look at those? What are the E naught values associated with the silver ion and the cobalt ion? 0.79 .799 volts, good, and negative .277 volts, good. So right off the bat, we can assign the more positive value to be the cathode, and according to Red Cat, this will be where our reduction occurs. This will be the anode. This will be where our oxidation occurs. And we normally put our oxidation on the left. We put our reduction on the right if we were going to be drawing this out in terms of a full picture for the voltaic cell. But it doesn't ask us to do that. So write the half reactions. Okay, so could you give me the half reaction for our oxidation? Yep, yields. You got it. CO yields CO2 plus 2 electrons. And what about, I'm just going to write here, E naught here is equal to negative .277 volts. And what about for the cathode? Plus yields. You got it. And the E naught here is going to equal .799 volts. Okay, now to figure out our E naught for the cell, we can do E naught reduction at the cathode minus E naught reduction at the anode. And remember, the term reduction there is because they're always written as reduction half reactions within the tabulated tables. So for this, we can go ahead and plug in what we know. We have .799 minus a negative .277. Go ahead and crank out the E naught for the cell. .076, so 1.08. If we get it around to. Okay. I guess because we're dealing with subtraction, we can actually take it out to 3 sig figs after the right of the decimal place. So 1.076 is what we'll call it. Okay, let's try another. Let's just say here that a voltaic cell is based on the following half reactions. And the first one is ion plus yields ion plus 3 plus 2 electrons. And the second one is Br2 is going to be added to 2 electrons to yield 2 Br negative. And they tell us that the E naught for the cell is equal to 1.46. They tell us the E naught reduction for the bromine is equal to 1.06, and they want us to find the E naught reduction for the ion half reaction. So again, we're going to use our equation here that E naught of the cell is equal to E naught reduction of the cathode minus E naught reduction for the anode. And where do I put my numbers? Good, so the 1.46 goes here, set it equal to say 1.06 volts minus X. Solving it for X, we're going to get negative 0.40 volts. Now, how did we know that the 1.06 fell under the cathode? It's what? Perfect. It is what is getting reduced. You got it. So, because it is getting reduced, that is our cathode. You got it. Nice. Okay, let's try one more of those. Okay. Calculate the E naught for the cell. Hey, Carpy. That involves the overall reaction of 2 aluminum solid plus 3 I2 solid yields 2 aluminum plus 3 plus 6 I negative. And these would both be aqueous. So we need to find the E naught for that cell. And what we want to do here is basically figure out the half reactions. Once we figure out the half reactions, we can go look up the E naught values for each half reaction and then use our standard equation to find the E naught for the cell. So let's go ahead and write oxidation numbers. The oxidation number for aluminum would be 0, I2, 0, Al plus 3, and 6I negative, negative 1. Looks like our aluminum is climbing, so there's our Leo. It looks like our iodine is dropping. There is our Ger. Okay, so if we had to write our oxidation half reaction, how would you do it? Yep. Good job. And our reduction? I love you, Colin. For the reduction, you always go with what is your first one on your reactant side. So 3. Yep. Yep. You got it. You got 3 I2 plus 6 electrons would yield 6 I negative. Okay, now let's go and find in our table the E naught values for those two reactions, or two half reactions. So take a second to look those up. Let's figure out our E naught values. Find them? Yep, negative 1.66 volts. And the other? What is it? 0.536 volts. Good. So now we employ our equation, E naught of our cell will equal E naught reduction at the cathode minus E naught reduction at the anode. So which one of these is our cathode, which one is our anode? Okay, so reductions are cathode, so we're going to have our 0.536 minus a negative 1.66, and that's going to end up giving us 2.20 volts for our cell. Okay, spontaneity. If we end up having E naught being a positive value, that is going to equate itself with a spontaneous reaction. E naught negative, reaction is non-spontaneous. So anytime you have a reaction, and I'll give you one here, let's say we have I2 plus Cu plus 2 plus 6H2O yielding 2IO3 negative plus 5 copper plus 12H plus. If we assign oxidation numbers here and write half reactions, we would have 0 plus 2 plus 1 minus 2 plus 5 negative 2 0 and plus 1. Looks like our iodine goes from 0 up to plus 5. That is going to be our Leo. And our copper drops from plus 2 down to 0. So that is our Ger. So if we utilize the half reaction method, we have I2 yielding IO3. Let's see if we can, it was 2IO3. Let's see if we can figure out the half reaction here using what we basically did with our acidic medium. So if we want to balance this, the half reaction at least, first thing we need to do is balance things other than I, or O and H. We're good because I is balanced. Next, we can go ahead and balance our oxygen. So what do we have to do to balance oxygen? And careful because we got a 2 already there. Yep. So we'll add 6H2O to the left. Then we have to add what? 12H plus to the right. Good job. And now, how many electrons are we dealing with? What's that? 2 negative, 12 positive. So we've got a positive 10 here. Okay, so we've got positive 10, so we have to add, very good, our 10 electrons. We're 0 here. Now we are at 0 here. Good. And then for our copper, we have Cu plus 2 going to 5 Cu. So we're going to have to add a 5 also to this side. We've got plus 2, 0. So over here we have to add how many? Just because we had 5 copper there, so I took it over. Yep. So it looks like we have to add, careful, 5, good, add that there. Okay, so now we should have hopefully a balanced equation here. Go ahead and let's look up these two values in our table E to find our E naught values. What do we got? .85 what for the copper? Okay. I got 1.195 for the iodine. Did I do it wrong? Am I right? Okay, 1.195. What'd you get for the copper? It's like .337. Or what's that? Okay, good. So now, okay, we know that this is our oxidation. This is our reduction. So if we want to find E naught of our cell, we're going to take our cathode first, red cat, so our .337. We're going to subtract out our 1.195, and we'll get negative .858 volts. And what this means is this reaction will be non-spontaneous in the forward direction. How could we make it, or what is spontaneous? Yep, it would be spontaneous in the reverse. Alright, so it's non-spontaneous in the forward, but it would be spontaneous in the reverse. Okay, last part for today is relating now our Gibbs free energy, delta G term, and our voltage, or electromotive force. And we can relate that with the equation that delta G is equal to negative NFE. And delta G naught, standard conditions, will equal negative NFE naught. A couple things to remember. N is equal to the number of electrons transferred in the process. F is equal to Faraday's constant. So 1F is equal to 96,485 coulombs per mole. And E, what's that? Good question. You can also express this as 96,485 joules over volt, joules for volt mole. That is an equivalent expression. Want to check it? Okay. So yeah, I'm glad you mentioned it though, because these are equivalent. How are they equivalent? I don't know. Let's see. 1 joule is equal to a volt times coulomb. So if we put volt per coulomb now. So volt per coulomb over volt per mole. Volts cancel, and we're back to coulombs per mole. So it does work. Now remember also from last chapter, we have the equation delta G naught is equal to negative RT ln of K. So sometimes, let's rewrite that. Delta G naught equals negative RT ln of K. Sometimes what they will do is they will ask you to find the equilibrium constant K from an E naught value. So you have to first find delta G, then once you find delta G, you can solve for K. Okay, let's do one of those problems, and we'll call it a day. Last one. This is practice exercise page 864. Says for the following reaction, we've got 3 nickel, 3 Ni plus 2, plus 2 Cr OH3, aqueous solid, plus 10 OH negative. We're yielding 3 nickel solid plus 2 CrO4 2 minus plus 8 H2O. So for that reaction, it says what is the value of N? B, find delta G naught, and C, calculate K at 298 Kelvin. Okay. First thing we need to do here is essentially write our two half reactions. So plus 2, we've got negative 2 plus 1. Chromium will be plus 3. Negative 2 plus 1, 0. Negative 2. Chromium will be what? Plus 6. Oxygen negative 2. And hydrogen plus 1. All right, what is going to be our oxidation half reaction? What gets oxidized? Looks like we have a drop where? Nickel? Yeah, I'm seeing. Oh, that would be our GUR. Nickel would be our GUR. What goes up? Chromium. There we go. Yeah. So we've got essentially here. Well, we can start with either one. Let's start with reduction. So for our reduction, we've got 3 nickel plus 2, yielding 3 nickel. So to balance this out, we've got to have 6 electrons added over to our left-hand side. And then if we do our reduction, we've got 2 Cr OH3 solid, yielding 2 CrO4 2 minus. Chromiums look balanced, but oxygens do not. Hydrogens do not. So let's start with oxygens. Looks like we have a total of 6 on the left. It looks like we have, what, 8 on the right?
So the first one, the reduction.
What's that?
Yeah,
Oh, yes, I do. Thanks. Good eyes. we need to add some water. How much and where? We're 2 oxygens short, so we need 2 water molecules added to the left. So 2H2O goes on the left. Now it looks like we have a total of 4 hydrogens plus 6. So we need to get how many hydrogens added to the right? Yep, 10H plus added to the right. Now we can balance with charge. Looks like on the right we have 2 times -2, -4. So it looks like we have +6. 0 on the left. We've got to knock that +6 down. So there's our 6 electrons. So thankfully they agree. We don't have to multiply through by a coefficient. And our N value for A will equal how many electrons? 6. Okay, we're ready now to, in B, find delta G naught, and we can do that using -N F E naught. So in order to do that, we've got to find our E naught for the cell. So let's go, I will give you the values here. We've done enough of these, you don't have to look them back up. So our reduction occurs at the cathode, and this is -0.28 volts for this E naught value. This E naught value is equal to -0.13 volts. So now to find our E naught for our cell, we'll take our -0.28 volts, subtract out a -0.13 volts, and we will end up with -0.15 volts for our E naught value. Now we have what we need to solve for delta G, so we can plug and chug. 6 electrons times our 96,485 coulombs per mole of electrons. This stands for 6 moles of electrons right here, multiplied by our 0.15 volts. And like you had said earlier, this can also be written as joule per volt mole. So I'm going to actually, the only reason I mention that is because that's how you can see how volts cancel, to give you no units, because delta G is unitless. Working that out, we're going to get 87 kilojoules. And now in C, we can calculate our K value. We know that we have 87 kilojoules will equal negative 8.314 joules per mole Kelvin times our 298 times the ln of K. And before we get into unit problems, let's go ahead and change this out of kilojoules into joules. So we will say 87 times 10 to the third joules is equal to negative 8.314 joules per mole Kelvin. Solve it for K, and I'll let you do it, but you should get 5.6 times 10 raised to the -16th